So I'll be here solving this conservation of momentum in the x and y direction for Tuesday's homework. So here you can see we got two objects coming in. One's coming in this way and one's coming in this way. And they're going to stick together. Now, just logic tells you that if one's coming in that way, one's coming in that way, that they're probably going to go off in some direction, off possibly in this direction maybe. So the question here is, what will be the new velocity and direction of the mass after the collision? So we're going to have to consider the two objects, their momentum in the x and y. So I'm going to start with object m1. So let's do that right here. It is coming in at, looks like 30 degrees. And now, of course, that has px1, py1. And the m was 3. And the velocity was 6. Okay, so px1 is going to be 3 times 6 times the cosine of 30. And that is going to be cos 30 times 18, 15.59. Oopsies. Interesting fact about me is that my hand hiccups when I have to write fives. I don't know why. It has always been that way my entire life. So sometimes I have to concentrate to make fives. But you'll see that sometimes as I write that I have to constantly erase my fives if I go too fast. So py1 is going to be 3, 6 sine 30, and sine 30 is a half, so that's 9. So, all right, that takes care of px1, py1. Let's do the same thing for m2. M2 coming up like this. And m2 is 2 kilograms with a velocity of 5 meters per second. That's not too bad. And the angle was... Okay, now a little bit interesting here. They give you the angle over here as being 50 degrees. Now that does not correspond to the triangle I made. I made this triangle here, right? However, through a couple of the law of, well, there's a geometric law. If you have two parallel things like this angle is equal to this angle. So this is still 50. Anyways, so now we can figure out that px2 is going to be 2, 5 cos 50. And py2 is going to be 2, 5 cos 50 equals, so 10 cos 50, 6.43, oops, not meters per second, kilogram meters per second. This is momentum. And this is 10 sine 50. I see that I'm going to have to quickly change that. 7.66. Okay. So now we know that the px final of this final object is going to be, it looks like, okay, so at this moment right here, we're going to pause for a second, and this is something that you probably caught early on, but this is something that sometimes I just catch at this stage here. It just depends on, at this point, when I'm trying to add up all the net momentum, I start to look often at, I double check the direction of the momentum. And here, I know that m1 has a negative momenta in the x direction. So if I didn't put it on before, I better put it on now. And again, This is something I usually double check at this stage because when you're adding your net momenta, the direction matters. So we're going to have negative 15.59. Now this M2 is going to be positive, and so that's going to be plus 6.43. And that is going to be 6.43 minus 15.59, a negative 9.16. The PY final, again, same deal. This is sort of where I double check my directions. I noticed that M1 better be a negative. So if I didn't put it on before, I better put it on now. And the P2Y is going to be a positive. So this is going to be a negative 9 plus 7.66. So 1.34. Negative 1.34. Okay. Now I can start to figure out the momenta of the final object that has now been stuck together. It is going to have... let's go red now. No, let's go blue. The final object is going to have an x direction momentum of negative 9.16. It's going to have y momentum of, in this case, negative 1.34. So the actual object is like this. So in all of our three options, it actually is going to go off somewhere like this. Again, not unexpected. So the final momentum, the P final of this object is going to be 1.34 squared plus 9.16 squared. Take the square root. 9.26. It's asking for the new velocity in the direction. Okay, so it is a combined mass. So 9.26 has to equal the combined mass, which is 3 plus 2 times VF. 1.85. And the angle is going to be the inverse tangent. Inverse tangent of 1.34 divided by 9.16. Looks like a pretty shallow angle here, 8.32 degrees. So inverse tangent of 1.34 all over 9.16. That seems a little shallow to me, but you know what? That's what the calculator tells me. 8.32. Okay, so we're good on those. So the next question is, if 35% of the energy is lost due to crushing the objects together, what is the new velocity in this case? Notice that 35% of the energy is lost, not 35% of the momentum. Okay, so we're going to scroll down here for a little bit, and I am actually going to take advantage of this tool. I lied, that's the wrong tool. Okay. Oh, no. Okay. So the kinetic energy in the beginning. So KE total is going to be 1/2 m1 v1 squared plus 1/2 m2 v2 squared. 1/2 m1 was given as 3 and its velocity was 6. M2's mass is 2, its velocity I think was 5. Yeah. And so now that total kinetic energy of the system is going to be 36 times 1.5, 54, plus 25 times, well, just 25. All right, total energy of 79 joules before the collision. After the, it says that 35% of that energy is lost So if we lose 35%, we keep 65%. So 0.65 times 79. So 0.65 times 79, 51.35. Okay, so this is how much kinetic energy we're going to we have left over after the collision. Now the object is stuck together. So the 1/2 m1 plus m2 has to equal this new reduced kinetic energy. So 1/2 5 VF squared has to equal this 51.335. And now we can solve for VF. So 51.35 divided by 2.5, take the square root, 4.53. This seems off to me, but you know what? Okay. This is going to be where I cut this video. Okay, this is a continuation of the problem. So I paused briefly because when I solve for the velocity of the object, if you lose 35% of the energy, here you can see the kinetic energy of both objects. That's a total of 79 joules, and then 65% of that is 51.35, and so I set that equal to the final kinetic energy, and you get a final velocity of 4.35, and then you compare that to up here. The final velocity when you do conservation of momentum is 1.85. So what's happening here, and that's why I paused, I was thinking to myself, how could the final velocity, if you lose 35% of your energy, be 4.53 meters per second when the actual answer is 1.85, right? If you lose energy, shouldn't it be less than 1.85? Double check my work, and it just occurred to me that this is an inelastic collision, and so energy is of course lost in order for these objects to stick together. When you assume that only 35% of the energy is lost, you will get a final velocity of 4.53. However, the fact that the actual velocity of the objects, when they stick together, the actual velocity of the objects, and this is a true momentum question, is 1.85. That tells you that the actual energy lost when you have these objects collide is much higher than 35%. Adjusting it to 35% makes it less energy loss, and so that's why this number is higher. In fact, I did the math real quick. It turns out I don't want to say real life, but in the actual problem as written, approximately 90% of the kinetic energy is lost in order to bind these two objects together. It's actually a 90% energy loss, and then when you get down to question B, it's saying, hey, what if it's only 35%? So that's how we want to read that. It's totally reasonable that you would second guess and that you would double check, but again, hopefully this is illustrative of that when you're doing physics, you always have to look at your final answer and ask yourself, does it make sense? At first, this did not make sense, that it was 4.53 meters per second, because how could it be higher if you have 35% energy loss? But then when you double check your work and you have faith in your math, then you have to start to explain it to yourself. Okay, the math don't lie, right? So what is wrong in my understanding that that I'm getting an answer that doesn't make sense to me? And again, you have to be careful that your math does make sense. And so sometimes I have a tendency to go too quickly and make a simple computing error when making these keys, so I had to slow down a little bit and double check my math. But I do have faith in the math, so you have to ask, okay, so what's happening here? And then as soon as you accept, oopsies, that these values are correct, then you have to try to explain it. And the only explanation, or the correct explanation that you have to stumble upon, is that, okay, that there actually must be quite a ton of energy loss in this collision, and that when question B says 35, that's actually making less energy loss than it truly is. And in fact, there's actually approximately 90% 90% kinetic energy loss in this collision. So anyway,